Hey guys, welcome back. Today we're going to be talking a little bit about radioactivity, also known as radioactive decay. So let's begin with a little bit about how radioactivity was first discovered. Way back in 1896, a French scientist named Henri Becquerel was examining the decay of a certain uranium mineral. And the prevailing attitude at this time was that something specific was happening to this uranium. And we knew something was happening, but we weren't quite sure exactly what was. Prevailing attitude at the time was that it was X-rays coming out of the sun that was absorbed by the uranium and was re-emitted. However, this became a little bit problematic when he realized that the plates he developed on overcast day and after wrapping the uranium mineral in like some kind of covering still lit up bright as day. So he knew something else had to be up, and to do this, like any good scientist, he devised an experiment. So what he did here was he had a radioactive sample that he put right over here, and right from there, radioactive decay, whatever could it be, would shoot out of there and interact with this magnetic field. Now, the special part about the magnetic field was that if there were any light rays or X-rays coming out of it, as the previous attitude had predicted, then they wouldn't be bent by that magnetic field. But if it was charged, if this radioactive decay had some kind of electric charge, then they would be bent a little bit. And that's exactly what he discovered, that once this radioactive sample decayed, he discovered various kinds of particles were bending when he put them in this magnetic field. Now, you don't have to worry about the magnetic field too much because we haven't covered that in AP Physics 1, but just know that charged particles do have a force applied to them when they're in the magnetic field, and that they would cause the paths of these molecules to bend. And fun fact, the SI unit of radioactive decay is named the Becquerel in honor of this. So, of course, you can see these Greek letters here, and later on, Marie Curie, along with her husband Pierre, ended up isolating two elements that were highly radioactive, and they're now called polonium and radium. And Marie Curie was the one who coined the term radioactivity. Later on, Ernest Rutherford, he of the cold foil experiment that you might remember from last lesson, classified these different kinds of radioactive decay by how far they could penetrate several different substances. So 3 types of radioactive rays were found. Alpha rays barely penetrated a sheet of paper when you set it in front of the ray. Beta rays could penetrate around 3 millimeters of aluminum, so they could penetrate aluminum foil. A little bit thicker than aluminum foil, actually. Then gamma rays were so powerful that they could penetrate several centimeters of lead, which is pretty crazy. And today, we now know that alpha rays are made of helium nuclei, or the nucleuses of helium, and beta rays are electrons, or positrons, as we're going to talk about in a little bit, and gamma rays were electromagnetic radiation, or photons, also known as light. So let's talk a little bit about alpha decay. Alpha decay is represented by this Greek letter over here, the Greek letter alpha. And an example of alpha decay is when radium-226 decays into radon-222, as we can see here. Radium on the left, decays into radon plus this helium. This helium here is actually a helium nucleus. There's no electrons coming off of it, and is also denoted by the Greek letter alpha, which, by the way, you can write on the test if you like, instead of writing 4-2He. Now, this is an example of transmutation, which is the change of one element to another. Now, transmutation is kind of a whack thing because this was something that alchemists were trying to do. Way back in the day, the whole goal of alchemy was trying to convert lead to gold. And this was previously considered impossible by modern chemists who were, of course, trying to be independent, scholarly individuals. So when transmutation was first discovered, when thorium was converting to radium, one of the scientists, Frederick Soddy, shouted out, "Rutherford, this is transmutation," to Ernest Rutherford, who was also a scientist working on this. And then Rutherford snapped back, "For Christ's sake, Saudi, don't call it transmutation. They'll have our heads off as alchemists." Well, it turns out that reality is a little stranger than science. And if you're wondering if this means that you can make gold from lead, yes, you could, but it is so cost prohibitive that it would be much, much more impractical than to actually just get gold yourself from the earth. Anyway, back at alpha decay, we can see that the alpha decay process is written like so. A here represents the atomic weight, of course, and Z represents the atomic number. And it turns into a new element with atomic number Z minus 2 and atomic weight A minus 4 with this new helium over here. Now, alpha decay occurs when the strong nuclear force can't hold a large nucleus together, which tends to happen the larger a nucleus gets. The mass of the parent nucleus is, of course, greater than the sum of the masses of the daughter nucleus and the alpha particle, and this difference is called the disintegration energy, which you might remember from last lesson. That occurs because there is a little bit of mass that is lost in the form of energy. Alpha particles themselves are quite stable because helium themselves are quite stable, and they have a mass of 4.002602 units. So first, let's look at this equation. We're going to calculate the disintegration energy from when uranium-232 decays to thorium-228 with the emission of an alpha particle. Well, all we have to do here is remember the equation we did from last unit. E is equal to delta mc squared. Now, for whatever reason, the disintegration energy is denoted as Q, so we're just going to write it as that. I don't know why. But Q will be equal to the change in mass. So the mass will be the mass of the parent nucleus, which would be uranium-232 in this case, minus the mass of the daughter nucleus, which would be thorium-228, minus the mass of the alpha particle. And when we do this math, we can see that, hold on, let me get this over here, that uranium, that if we do this, we can see that 232.037131 minus 228.0287116 minus 4.002602 times C squared. And if we do this all out, we can find that this is equal to 0.005813 units. And since we know that to convert from units to atomic energy, we have to multiply it by 931.5 mega electron volts per unit. We know that the total disintegration energy will be around 5.4 mega electron volts. And there is our final answer. And this kind of alpha decay is actually highly relevant to how smoke detectors work. There's a video like this in the PowerPoint, but to give a quick summary of it, smoke detectors work like a tripwire. So what we have here is a source of alpha particles that emit alpha particles and ionize the ions in between here and cause a little electric current to flow. Once smoke particles come in here, this gap, they absorb the alpha particles and they block this current. And the sudden drop in this current is measured by this current detector. And when they do that, they know that something is amiss and they'll sound the alarm. In fact, the active element inside these smoke detectors is americium-241, which decays to neptunium, whose atomic weight is 237, plus alpha particle. This is the decay that occurs. This is a really interesting one because we tend to think of elements that are beyond uranium as being super exotic and really hard to buy. But in reality, there's probably some americium at your house guarding you from some fires. So let's move on and talk about beta decay. Now this one is a bit of a lengthy one, but just stick with me, we'll get it through it. Beta decay occurs when a nucleus emits an electron. So transmutation also occurs in beta decay. As we can see, this carbon-14 is being turned into nitrogen-14. And it emits one electron and a neutrino, which we're going to talk about in a little bit. The final nucleus, remember, still has 14 nucleons, which is why the atomic weight is still 14, but it has one more neutron and it has one fewer neutron. One more proton and one fewer neutron. This decay is an example of an interaction that is caused by the weak nuclear force. Now, that's pretty much all you have to know about the weak nuclear force. Again, from last unit, it's a little confusing, but just know that the weak nuclear force causes beta decay. Now, an important note here is that the electron in beta decay is not an atomic orbital electron. It actually comes directly from the nucleus. The nucleus itself yeets this electron directly from the nucleus. And that's why we call them beta particles, so we don't confuse them with the orbital electrons around the nucleus. So let's do a little bit more problems over here. What is the energy that is released when carbon-14 decays into nitrogen-14 by beta emission? So we know that we're trying to find the change in mass that occurs. So we know the change in mass is just equal to, well, let's think about it here. We know that carbon-14 initially has a mass of 14.00 3242. So this is our carbon-14 mass. And our nitrogen-14 mass is, where is it? Over here is 14.003074. Here's our times c squared. Well, this is the change in mass, so we're not actually going to worry about that. Now, if we do the math, we can see that the change in mass difference is 0.000168 units. And if we convert that into mega electron volts using 931.5 MeV per units, then we know that this E is equal to 0.156 mega electron volts, or 156 kilo electron volts. Whoop. Okay, so scientists now have a problem. Careful measurements showed that these released beta particles, when they were measuring this specific reaction, should have a kinetic energy of around 156 kilo electron volts. But we noticed that that wasn't the case. Although some beta particles did have that atomic energy, more often than not, they would have much, much less kinetic energy. And more experiments showed that they also didn't have the correct angular and linear momentum. Something was happening. So, although some scientists proposed that maybe the laws of conservation of energy or momentum didn't apply in this case, people were kind of reluctant to give that up because, you know, they were really helpful in the past, and it would be a shame if they had to go. Then, one scientist came up with an idea. Wolfgang Pauli proposed that a new particle would form in this reaction, and that Enrico Fermi decided to name the neutrino, which means the little neutral one in Italian. And indeed, this is what's happening. We know that some particle has to gain all that kinetic energy and momentum. So we can see here that the fundamental process of beta decay is indeed this neutron, which decays into a proton, electron, and a neutrino. Now, neutrinos are really weird particles. They're really difficult to detect. In fact, neutrinos produced by the sun are passing through your body every second, around trillions of them. And you can't feel them because they just pass directly through things. We know they travel at the speed of light, and we know that they're massless. And direct evidence for their existence wasn't available for more than 20 years until they were predicted. These were very, very slippery snails. The symbol for the neutrino is the Greek letter nu, here denoted by this weird V-looking thing. That isn't a V, I promise you. And this is the beta decay that occurs in carbon-14 to nitrogen-14. Now, this little bar above neutrino means that neutrino is actually an antineutrino. It's antimatter. And we're going to talk a little bit about that over here. Because beta decay can also occur when the nucleus emits a positron rather than an electron. Now, I'm sure you've heard a little bit about antimatter. That antimatter is kind of like the reverse and the opposite of actual matter. And indeed, that's something that occurs when beta decay occurs. Whereas in the past, we can see that a negative electron, which is a normal quote-unquote matter electron, and an antineutrino, which is the antimatter version of neutrino, is formed. Oops. Then here, a positron, which is an antimatter electron, is produced, and a normal neutrino is also produced. And we can see here that instead of the atomic mass gaining 1, the atomic mass loses 1, as you can see here. So this is actually known as beta plus decay. The previous decay is notated as beta minus decay. It's also written as the beta symbol with a little superscript minus sign. And this is beta plus decay, or the beta symbol with a plus sign, superscript. And I know I said before that a beta decay comes directly from the nucleus, but a nucleus can also capture one of its inner electrons and then turn into another element while also emitting a neutrino. For some reason, electron capture is somehow considered a beta decay, even though it really isn't, but just know that electron capture can happen. This electron comes directly from the inner orbital of the nucleus, which is pretty crazy. Lastly, we're going to talk about gamma decay. It's also known as gamma emission for reasons that will become obvious. Gamma rays are very high energy photons, or light particles. They are emitted when a nucleus decays from an excited state to a lower state. So here we see on a diagram over here. You might have remembered from chemistry that that electrons within energy levels can jump to higher excited energy states, and when they drop back down, they'll emit some kind of photon or light energy. The same thing can happen with nuclei. In this decay from boron-12 to carbon-12, we can see that there are two different paths the nucleus can take. It can make one beta minus decay directly with 13.4 mega electron volts directly to carbon-12, or it can decay a little bit to 9 mega electron volts to this excited energy state. And when in this excited energy state, the excited carbon-12 will emit a 4.4 mega electron volt gamma ray that comes directly from the nucleus that will then result in the unexcited ground state carbon-12. And this little asterisk here just represents that the nucleus, is in an excited state. And here's the equation that we use to denote gamma decay, right over here. We just use a little asterisk to denote that it is excited and that it just drops back down to its normal energy, to its normal ground state. It makes no change the atomic number or the mass number. I pulled this slide off of online, and it came with this delightful picture of Keanu Reeves, which illustrates the point precisely. Just as with Keanu Reeves, gamma decay does nothing to this atom. It really just changes its energy state. And of course, I'm going to briefly mention this thing called internal conversion, sometimes similar to what happens in electron capture. An excited nucleus will grab an orbital electron and eject it with the same kinetic energy as the gamma ray would have had. This is also known as internal conversion. In this case, this isn't the same thing as electron capture because this doesn't emit a neutrino. Okay. And if you're wondering, you might have also heard of X-rays. Gamma rays and X-rays are kind of similar, even though they are called different things. So let's go over that briefly. They're both very high energy, but the main difference with gamma rays and X-rays is how they're produced. They have roughly the same wavelength, as you can see over here, but gamma rays are, of course, produced directly from the nucleus, as you can see over here, while X-rays are created when the electron and the nucleus interact over here. And lastly, we're just going to briefly touch that you shouldn't have noticed in these conservation laws, that these kind of radioactive decay conserve nucleons. So these nucleons the total number of nucleons can never change in between these. You can see that in alpha decay, these the A-4 and the Z-2 go away in the form of this helium. And in beta decay, even though you'll notice that the atomic weight stays the same from here to here. The electron we don't really count in this term because it isn't a nucleon, and the neutrino isn't a nucleon. And in gamma decay, of course, everything stays the same because neither the atomic weight nor the mass changes. Sorry, the atomic number nor the mass changes. So to briefly sum up, radioactivity, which is also known as radioactive decay, occurs when unstable nuclei split apart, or decay. There are three types of radioactive decay: alpha, beta, and gamma, and nucleons are conserved in between decay. Also, the total number of nucleons basically remains constant in between. I have this nice picture over here that summarizes all the different kinds of alpha decay. Just to summarize it all up, it's on the PowerPoint if you want to see it. All right, that should be all from me. This is Stephen Hu signing off.